that goes inside the square root. Okay? And you're going to get a plus b plus minus that all over 2a. Okay. Will you ever get an imaginary number? No, it's always positive or 0. Okay? So, yeah, if you took 10, you should have seen some examples where you will get imaginary eigenvalues. So you're not guaranteed that they're always going to be real. Okay? But for a symmetric matrix, it's actually always true. Okay? That the eigenvectors, even if it's not 2 by 2, even if it's 3 by 3 or 4 by 4, that's the amazing thing. It's a very deep theorem that it's asymmetric. Then all the eigenvalues are real. Okay, you're never going to get an imaginary eigenvalue. It's not at all obvious. If you have my book, that's the reason why there's chapter 8. It takes an entire chapter to prove it correctly and completely. Okay? So, what I wanted to start out with is maybe give you an example where the eigenvalues are a little bit nicer. Okay? So, Laurel, give me an integer.
4.
4. Okay, so I'll fill that with 4.
I'm just going to keep saying 9.
Okay.
Just so he can write more G's on the board.
Okay, and where's that? Okay, let's see if this works. You put a 9. Oh, you got your wish. Let me see if this
Yay.
works. Compute matrices. Oh, look at that.
That was all me.
Okay, any nasty square roots? No. Ooh, magic. Would you like to see another trick?
Would you like to show us it?
No, of course not. Here you go. Give me another. Oh, sorry, give me another. 5. 5. And, okay. 10.
Okay, let's see the pattern.
Wait.
What the heck?
What the heck?
Wait, that one?
Compute matrices eigenvectors. Oh, there it is.
Okay.
It's rigged.
Okay.
It's rigged.
It's rigged. No.
Oh, come on,
Okay.
you say it all the time.
Okay. So I'll tell you the secret. Okay. This is a little bit slightly more advanced math, although it's still undergrad math. Okay. You ever see this? Something squared plus something squared
Yeah.
equals something squared? In what famous theorem? Pythagorean theorem. Okay. So we know that there are some integers where, if you apply that, even the hypotenuse is going to be an integer. Okay. Like 3 squared plus 4 squared is
5 squared.
5 squared. Okay. So if you actually know a little bit something about that, you can make these kinds of matrices. Okay. It's really not that tricky. Okay. However, there's one thing else I want to point out here. Okay, look at the eigenvectors for the two matrices. Okay, check these out.
Negative reciprocals.
Let's see if you can see the relationship.
Your inverse. They both have the
But between the verses, the two. Well, between this one and this one. Well, I don't think he just means between the two. Between 5 has and 2 bits. I think he means
Thank
between
you. Sean got it. They are perpendicular to each
the-
other.
Oh,
Oh, he does.
That's a big difference. That's a
Oh,
big
I see.
difference.
Okay, but you were doing slope. Okay, sorry.
Yeah.
Okay. They are perpendicular to each other. Okay, that is correct. That is another special property of symmetric matrices. Okay. Furthermore, okay, if V1 is from one eigenspace, lambda 1, and V2 is from a different eigenspace, lambda 2. Okay? If you have two distinct eigenspaces, then V1 dotted with V2 is 0. Yeah. Magic. Okay, magic. So let me demonstrate that one more time to you. Okay, and in fact, I prepared a gorgeous 4x4 example. So, and this is another example where Pythagorean pressures show up. Okay, 5 squared plus 12 squared, 13 squared. Okay, very, very special. Okay. Is it symmetric? Yeah. Okay, so 5 and 5, 12, 12, 12. Okay, symmetric. Okay. Flip it. Let's see. Okay, so yeah, let's do it one step at a time. You get to appreciate the computation. Okay, so first let's compute the parameter polynomial. So some big nasty thing. Okay, but if you try to solve it, okay, let's set it equal to 0, and then compute, solve exact, boom. Okay. Yeah, there are 4 distinct eigenvalues. Okay. So, okay. What do you know about diagonalization? Okay, if you have a 4x4 matrix and all the eigenvalues, there are 4 different eigenvalues. It can or cannot? It can be diagonalized. Okay. So you're guaranteed at least, well, you're guaranteed 4 linearly independent eigenvectors. Okay. So continuing. Now let's look for the eigenvectors. Okay. So compute matrices eigenvectors. Boom. Okay. So let me put them all in the same line so we can appreciate them better. Okay. All right. So what do you call the 0 eigenspace? The null space. Okay. So it's just the kernel based on. Yeah. And we have a 12 for negative 13 and for positive 13. Okay. So check it out. Okay. Are these 2 vectors orthogonal? Yes. Okay. Are these 2 orthogonal?
Yeah. Doesn't have 0 and
Yeah. That's negative 1, 0, 0, positive 1. Okay, first and the last, negative 1, 0, 0,
so if it's 0 and
positive.
something doesn't have 0, it's got it.
Correct. So, and these 2, yeah, 0. Okay. 0, 0, 0, 0. This one's the trickiest one. 25 minus 169
Well,
plus
they're the
1.
same thing, it's like one of them is opposite signs. So.
Correct. Yeah, because it's over 144. So yes, all 4 pairs, all 1, 2, 3, 4, 5, 6 pairs are orthogonal to each other. Okay, so magic. Okay, so this can be diagonalized, right? So the recipe, if you remember, if you know it, okay, you put these 4 vectors together, and then you make a 4x4 matrix. Okay, so 1, and yeah, it doesn't have to be in any order, so we can take any order we want. 1, 2, 3, 4. Okay, and then we'll put it together. Okay, so concatenate, correct. That is the command. Compute matrices, concatenate. There we go. Okay, so that should be an invertible matrix, right? So compute matrices inverse. Boom. Oh, okay, so got a little bit nasty. 169 came out.
This is inverted.
So, okay, and as I tell my class, I can never remember where the inverses go. So I think of it as AC, I'm sure is the correct order. And the other one is C. Okay. So the inverse will go on the left over here. If you move this over, let's see inverse AC is C. Okay. So I will take, this is the inverse. Okay. I will copy the original matrix over here. And then the C will go on the right.
And it equals.
Okay, so if you multiply it all that out, what will be on the diagonal of that matrix? What will be the order that it appears? controlled by the eigenvalues.
Oh, so let's see.
0, 12, negative 13, positive 13. That should be the order. Okay. Drum roll. There you go.
Whoa.
Fancy. 0, 12, negative 13, positive. Okay. So that's nice, but
Why did we do this again?
what do we
If you already noticed it.
Yeah, well, demonstrate. Okay, but one of the frustrating things about Math 10 is that there's so much nice, beautiful stuff to talk about. And there's never enough time to it. So this is why I like these sorts of venues, because we can just talk and have fun and play around. And one of the gorgeous things about symmetric matrices is that the diagonalizing matrix can be made even more special. Okay, so what does that mean? I said I want to talk about a couple of special kinds of matrices. The first one being symmetric matrices. Okay, the other kind of matrix is called an orthogonal matrix. Okay? So a matrix, an m by m matrix Q is called orthogonal. If Q times its transpose. Okay? If you multiply Q by its transpose, just flip it. Okay? Shocking. You get the idea? Okay. So if you took my class or recently, or are taking it recently, you should know one of my favorite examples of a linear transformation where the matrix that you get is symmetric, and if you do it again, you get your original vector back.
Self-inverting?
Yes, you're in the right neighborhood. What linear transformation in space is self-inverting?
Isomorphism?
Reflections, okay? Reflecting across a line or across a plane, okay? So that is a good example. Okay? The matrix of a reflection operation across a plane or a line is an example, okay? It's symmetric, okay? So when you transpose it, you get the same matrix. If you reflect the vector twice, you get the original vector. So that's the identity isomorphism. Okay? So we can, with apologies to those who did not take Math 10 from me, or my book, obviously. Let's make an example. I have an example over here. Here you go. Okay. So I chose the plane 3x minus 5y plus 2z equals 0. Okay, so if you remember the recipe, you take the product of this matrix with its transpose, okay, and you will get 9 minus 15, 6, minus 15, 25, minus 10, 6. But to make the projection work, you have to turn it into a unit vector. Okay, so you divide by the square of the length. Okay, so that's 9 and 25 and 4 is 38. Okay, so you take that and you subtract twice of it from the identity. Okay, and this is the matrix of the reflection operation. Okay, across the plane. Okay, yeah. Nick.
Is there a way to think of like visually what orthogonal matrix is?
Oh, absolutely. Yes. Yes.
Okay.
Mm-hmm. Mm-hmm. How? Okay. So, yeah, let's just demonstrate that. Okay, does that look symmetric to you?
Yes.
Yeah. Okay. Same. Okay. So, it's equal to its transpose. Okay. If you multiply it to itself, you should get the identity. Okay. So if you took my 10, you've seen this demonstrated. If you square that, you are going to get, boom, identity. Okay? So that is an example of an orthogonal matrix. Okay? All right. How do you visualize what's going on? Okay, what kind of a transformation is this? Okay. All right. Well, here's an easy way to think about it. Okay. When you if you write the matrix into rows, you'll get that, right? Okay. So if you take the transpose, okay, what are you going to get?
Rows and columns.
Okay. So yeah, the rows become columns. Okay. So the row 1 transpose, okay, row 2 transpose up to Rn transpose. Okay, so row 1 becomes column 1, so we write that as row 1 transpose. Okay, so when you multiply that out, you're supposed to get ones and zeros. Right? So what does that mean? If you take row 1, multiply it by B, by itself, transpose, you will get 1. What kind of vector is that?
Orthogonal.
If you dot the vector with itself, and you get 1, you get
No,
1.
unit. You
It'd
get
be
one.
like minus
There's no such thing as a vector inverse, so.
It would be like taking like
Okay. So row 1 dotted with row 1 will just give you 1.
They're same thing
They're
are
one.
reciprocal.
The same
When you dot the
vectors.
vector with itself, you get its
Magnitude.
magnitude.
one.
So it's a unit vector. Row 1 is a unit vector.
McCarthy.
It's Friday. It's Friday. So row 1 is a unit vector. Row 2 is a unit vector. All of them are unit vectors. Okay? But you also get a bunch of zeros. Okay? So if you take row 1 and you multiply it to row 2 transpose, you're supposed to get 0. Ooh. Okay? So row 1 and row 2 are
Perpendicular.
perpendicular, orthogonal to each other. Hence the word orthogonal matrix. Okay? The rows are orthogonal, but they're not just orthogonal, they're unit vectors. Okay? So, yeah, are these orthogonal vectors? Yeah, 150 minus 90 minus 60, yeah, you get 0. Okay, and so on. Okay? Yeah, but back to next question though. Okay, so how do you visualize this mean? What's going on? Okay, so think of this, well, as a linear transformation. Okay, in fact, it's an operator. Okay, you're going from R3 to R3. Okay, so where is it? So we know that if you have an operator from R3 to R3, then the matrix of P, okay, what goes into column 1? All right, I'll do it again. P of E1, P of E2, and P of E3. Okay? Okay, so what's going on? You have 3 vectors, okay, I, j, and k, E1, E2, E3. Okay, and E1 goes somewhere. Okay, so E1 will go to that vector, 10 over 19, 15 over 19, minus 6 over 19. Okay, so it's somewhere. Okay, let's say it's over here. Okay, E2 will go to another vector, but it's also going to be perpendicular to this vector. Okay, so the second vector is going to be something like that. All right. The third vector is going to be perpendicular to both of them. So yeah, what's going on here? It's like, right, okay, these 3 unit vectors are going to go to another triple of perpendicular unit vectors. Okay, so So literally, okay, another way to visualize this is that, okay, that's my thing, okay, so when we graph linear transformations, okay, remember, the basic square, okay, turns into a parallelogram most of the time, okay, it can collapse into a flat nothingness, okay, but here, is there going to be any collapsing? No, okay, in fact, the cube will stay as a cube. Okay, so one of the things that orthogonal transformation is that it preserves the volume of your space. Okay, so it doesn't go bigger or small.
And this would still be true from R4 to R4.
Correct.
So all four vectors would still be orthogonal to each other.
Yes, all four will still be orthogonal to each other. So yeah, that is what was happening. That is what's happening. Oh, wait a minute. I'm getting ahead of myself. Where am I? Where is my 4 by 4? Yeah, here we go. Yes, so, except, okay, yeah. Right. Except these 4 vectors are not unit vectors, okay? So, actually, okay, now is a good time to go back to the big picture, okay? So I said I wanted to look at 2 special kinds of matrices, symmetric matrices and orthogonal matrices, okay? They're connected to each other, okay? So, what's the connection? We diagonalized this matrix earlier, okay? This matrix that we got, is it orthogonal? I don't think so because, well, this is the inverse. The inverse is supposed to be its transpose. Okay, maybe I should have pointed that a little bit clearer, okay? If you multiply by a matrix by another matrix and you get identity, who is this other matrix? It's inverse, okay? So, in other words, Q transpose is the same as Q inverse. Okay, and how special is that? Okay, very special. It usually takes like 15 minutes to invert a 3 by 3 matrix, right? And let's forbid a 4 by 4 matrix, right? You have to do Gauss-Jordan, okay? But this is very special. There's no work done that you need to get the inverse. All you have to do is flip the matrix. It's totally amazing. Okay? So, how can we apply that here? Okay, we have these 4 vectors. They're orthogonal to each other, but they're not unit vectors. Okay? So basically, all we have to do now is to turn all of them into unit vectors. The second is already a unit vector. You see it? Okay? This one is not. The first one is not. So first step is to clear the 5. So that's minus 12 and 5, right? Okay. And what's the length of that vector? 13. Okay, so let's divide everybody by 13. Voila, that's a unit vector. Okay. Next, do the same thing here. Clear the 12, right? So that's going to be a 12 here. And that's going to be a 5. And that's going to be a negative 13. Okay, now, okay, what's the
5
length?
plus 169.
Okay, so 5 and 140, 25 and that's 169, and another 169. 2 times 169, so 13 square root of 2. Okay, so we will divide now.
How much that there's
Just get a calculator.
We will divide by 13
338.
square root of 2. I need the square root right there. Okay.
That's one way to do it.
And it's supposed to be inside parentheses, right? Okay, so boom, copy, copy. Okay, the last vector is similar in skeleton, right? You have 5, 13, 12. Okay, so we will clear the 12. That's going to be a 5, that's going to be a 13, that's going to be a 12, and divide everyone by 13 radical 2. Copy, copy, copy. Okay, so we got 4 unit vectors. Okay, and we already know they're perpendicular to each other. Put them together, compute matrices, common cut matrix. Boom. Okay, so this is supposed to be an orthogonal matrix, right? So let's flip it. Oh, by the But if you take the transpose, compute matrices transpose, okay. The test is multiply them together, you'd better get the identity. Okay, so multiply.
On which side?
Oh, yeah. It doesn't matter which way.
Wait, what is this?
Remember, if AB is the identity, DA also has to be the identity.
Oh, yeah.
Okay, neato. Okay. So this matrix will not only diagonalize our A, it does so orthogonally. Okay, so do I have it in the correct order? Okay, the inverse, I erased it. AC equals CD, C inverse goes on the left, and C inverse is on the left, correct? So if I put the original matrix in the middle, then where am I? Right there. Okay, so keep your fingers crossed. If it's wrong, it's just in the wrong order. Okay, so boom. Okay, it is there. Okay. Okay, cool. So, oh yeah, I did mention that the second part of this theorem, the main theorem, is actually easy to prove. Okay, first part is hard. Okay, you need an entire chapter to prove it. Okay, this one is just one paragraph. Okay, but what's the idea? Okay, you're going to need to know something from chapter 2. Okay, if you take two matrices and you can multiply them, okay, they're compatible. That was the formula. D transpose is A transpose. Okay, so this is all that we need to prove this, and it's not obvious at all. Okay, all right. So let's let me get over there where the eraser is. Okay. So, it's nice if we can just go directly and say, I want to show that v1.v2 is 0. Okay, but this is one of those proofs where you actually do like an end run to get to where you want to go. Okay? So, here's the trick. Look at v1 dotted with a times v1. I'm sorry, a times v2. Okay, so not v1 dot v2 directly, but v1 dotted with a times v2. Okay. Okay. So what else are we going to need? Okay. When you multiply two vectors, one as a row and one as a column, you're basically taking a dot product, right? So if you have like a1, a2, a3, multiplied by b1, b2, b2, you're getting a dot b, right?
Yeah.
Okay, you get a1, b1 plus a2, b2 plus a3, b3. That's a dot product. Okay? Okay, so here's what we're going to do. We're going to pretend that v1 is in a row. Okay? And, okay, v2 is also in a row. I'm sorry. Let's think in terms of columns, okay? So V2 is a column. Okay, if you multiply A by V2, it will still be a column, okay? So that is what we will put over here, okay? That will be a column. But if you want to multiply it by a row, V1 will have to turn into a transpose, okay? So this is now a row vector, and this is a column vector, okay? Okay. So, what are we going to do? This is the dot product of V1 with AB2. Okay? Make AB2 a column, and then make V1 a row by transposing. Okay? Okay, this is a number. Okay? So if you take the transpose, it stays a number. Right? So what is V1 transpose AV2? Take that product and transpose it. Okay, so now you apply this formula. Okay?
It's V transpose, or
AV2
then just V1.
and then
And
you
then-
transpose,
and
and then times
V1.
V1, correct. Okay, without, because the double transpose
Is itself.
is itself, correct, okay? Okay, and now you do it again, okay? What is AD2 transpose?
V transpose.
V2 transpose times A transpose. Times V1. Okay, however, who is A transpose? It's symmetric, so A transpose is
A inverse.
A itself, okay? Not orthogonal, but symmetric, so A itself, okay? So this is V2 transpose A times V1, okay? However, matrix multiplication is associative, okay? So we can write this as V2 transpose A V1. Okay? Okay, so, big picture. Back to the beginning. What is A times V2? Oh, I'm sorry. Let's not forget. V1 is an eigenvector for lambda 1. V2 is an eigenvector for lambda 2. Okay? So what is AB2? Lambda 2 V2. Okay, so we have V1 transpose lambda 2 V2. Okay, so again, that's still a matrix product. Okay? How about here? What is AB1? Lambda 1 V1. Okay, it's a matrix product. V2 translation. A little sloppy in my notation. Like so. Okay? And these two things are exactly the same. Okay? So you have V1 transpose times V2 times lambda 2 is the same as V2 transpose lambda 1 V1. Okay? But what is V1 transpose V2? That's V1 dot V2. Right? V1 as a row